All right, welcome back to lecture 5, titled Constant Acceleration in One Dimension. So you'll recall that the definition that we had for the average velocity was just the displacement divided by the time interval, or delta x over delta t, where delta x means x minus some initial x value. Now, some people will write x sub f minus x sub I for final position minus initial position. I tend to use x naught for our initial position, and that's what x naught means here, and also t naught means our initial time. Usually we take that to be 0. It means that our ruler is lined up with 0, so x naught is 0. All right, now, I also want to consider a constant acceleration. And recall that if we have a constant acceleration, that means that every minute we're going to get an additional bit of velocity. So it could be that we get an extra meter per second of velocity, it could be we get an extra mile per hour of velocity, or we could get another zip, using the terminology we used in the last lecture, per second. So if we have a constant acceleration, then our velocity will be linear, right? If we start out at 0, and we have an acceleration of, say, 1 meter per second squared, and that's 1 meter per second. Then after 1 second, we're going 1 meter per second. After 2 seconds, we're going 2 meters per second. After 10 seconds, we're going 10 meters per second. That's what it means. And we talked previously about the instantaneous velocity versus the average velocity, and I said that you can get an instantaneous velocity by taking a small interval, right? So instead of thinking, well, what's the average velocity starting at t equals 0 all the way to some time t, down here, right? Instead, we could say, well, let's consider an interval around this point here. And I'm going to take the average. So it's a little bit of a later time and a little bit of an earlier time. So at this point, my velocity would be something we might call v naught. And then at a later time, it would be v naught plus the acceleration times the time. Because after the time interval, delta t, right, going from here to here, so this is t naught, by the way. I should write that, t naught. So this interval here is the delta t, which I'm going to define t naught to be 0, so we can just call this t. The constant acceleration we're experiencing, we just have to multiply that times the time and add it to our initial velocity. That's a special case for constant acceleration only. And if I do that, I can average these 2 points. Okay, I keep saying average velocity, but I haven't actually shown you an average yet. So let's make this into an average. Well, how do we average 2 things? We add them together. So I'll take v of t plus v naught, and I'm going to divide it by 2, because there's 2 things I'm averaging. And so what do I get? I plug in for v of t, which is v naught plus at plus v naught divided by 2. And just a little bit of algebra, we'll get that this is 2v naught plus at divided by 2, which is going to be equal to v naught plus 1/2 at. Now I'm going to use that. I'm going to write this equation and call it equation 2. And I'm going to note here that t naught is equal to 0, right? Therefore, delta t and t naught are the same thing, because delta t is t minus t naught. If t naught is 0, then delta t is just equal to t. And now I want to use this definition of average velocity with this equation that I have here that resulted from taking an actual average. And here's how I'm going to do it. I'm going to say delta x over delta t is equal to this average velocity, v naught plus 1/2 at. Now, I said before that t naught was 0, so delta t is really just t, right? I'm going to multiply both sides by t, giving me that delta x will be equal to v naught plus 1/2 at, all times t. So that's just saying that the distance traveled is the velocity times the time. Now all I have to do is distribute this t and do a little bit of algebra. Delta x equals v naught times t plus 1/2 a times t squared. Now delta x, you'll recall, is just x of t minus x naught. And that's equal to v naught t plus 1/2 a t squared. I'm going to solve this for just x of t. And so why am I doing that? Well, that gives me an equation that's a function of time that gives me the position in terms of the initial position, x naught, the initial velocity, and the constant acceleration that we're experiencing. Now, keep in mind, this only works, this 1/2 at squared term at the end here, only works if we have a constant acceleration. It would be different if we had some other time variation for the acceleration. And so this we'll call equation number 3. That's what we wanted to get. And this is the basic equation that we can solve lots of physics problems with. For example, we can say if we start at 5 meters from some reference frame, traveling with an initial velocity of 10 meters per second, and we travel for 3 seconds under an acceleration of, a, where a is some constant value, then how far have we traveled? But we can ask other questions too. We can say if we've traveled, some distance, x of t minus x naught can be our delta x, and so if we travel 10 meters with an initial velocity of a meter per second and an acceleration of a, how long does it take to travel that distance? And we could solve for t in that case to get that answer. So there's lots of things we can do with this equation. And in the next lecture, we'll talk about a special case where we can manipulate this and solve for the time it takes to fall from a tree, for example. So why is this useful? Well, because we'll find out later that, that the gravitational acceleration near the surface of the Earth is approximately a constant. And so we can use a constant value to calculate things related to falling objects near the surface of the Earth. And so that we'll turn the a into a little g, and we'll say that g is equal to either 10 meters per second. If we want to be more accurate, we might say 9.8 meters per second. If we want to use different units, we might say it's 32 feet per second. But that's the acceleration that you experience near the surface of the Earth, and it's a constant acceleration, approximately.